You anything last day that you would be late?
No, I don't know about that. I didn't receive any information from
You were there in last class, right?
no,
You were there in last class, right?
You mean today? You asked whether they asked class today or
What's that?
you asked whether he will come today?
Yeah, did he leave any message with you guys that he would be late or anything like that?
Wow, if that's the case, there's
Then
no
you
one
should
else.
receive something. Yeah, that's true. But anyway, I'm just asking in case he discussed with you guys last day. That's fine.
The syllabus said this week should be transformer and a bird. Yeah, this week. He mentioned bird this Tuesday, yes. He mentioned bird, so.
So you already presented your research stuff?
Yeah, I did that. Cool.
Did they grill you?
Well, technically, yeah, well, I guess, I think because he's doing more like mathematics and theoretical.
This is like part of this. So the the project is like 3 weeks. Right? Part of the project is we're going to need 2D coordinates of all these constellations. And make like a whatever add one.
Oh, for which one or another?
Exactly.
I thought you were saying, no.
Johnson? For what class?
Oh, the sickness.
You're talking. Oh, rare disease, like, like how many people have that?
Yeah, like,
And I'll put it like 12, whatever.
yeah.
I'm just like,
You got 6 days to do this.
the truck was a little bit more. 10 to
Yeah.
and then so treat is just big well.
I think they teach well. I think I can come. I think it's about.
Right.
But I don't know.
I think there's well, nice This is shown. Sorry, everybody. I think it was a lot better, or a lot worse than I thought it would be. Okay. That's when you join a team with. Okay. So all of a sudden information. Might be your lots of information. Okay. So I'll send a message to you a little bit. Okay. Thank you. Yeah. Oh, you're fine. Okay. So let's get going. I need to get connected to the internet here, and for some reason this is like stopped working. So 1 second while I figure that out. But any questions before we get going on today's? Not really a lecture, but discussion. Anything? Working through the proposals. I'll have that done by the end of the week, including the weekend. So hopefully that will give you enough time to get feedback and get going. Can't even join the guest number here. Let me shut out entirely. There we go. Okay, cool. So for today, we're just going to do kind of Q&A on what it's like to do machine learning, in particular deep learning, for work. This is really meant to be driven by you, like what your questions are. Garrett was interested in, maybe talking a little bit about like approaches to new problems, like how do you actually use all these tools? So definitely do that. And yeah, just basically just leave it open to all of you just to ask your questions and kind of see where the discussion takes us. So I'm trying to get some resources. It's actually working. So I'll just open it up. Go for it. Whoever wants to start.
Thank you very much. I have a thing of 3 questions. First is for the attention mechanism in the transformer. Is it just to calculate the pairwise similarity of the new one and the old ones?
Pairwise similarity with the query vectors and the key vectors.
Query vector and key vector.
Yep.
And the key vector is the old ones here. And the query.
Say it again.
So the query vector is a new one, and the key is the old ones. Yes.
Yeah, I don't know if old and new is a good way to think of it because they kind of like in the encoder they're all created at the same time, so that it's not old and new. In the decoder, the keys are coming from the encoder, the queries are coming from the decoder.
Okay.
Yeah.
And then use that to calculate the weight. Yes. Use the similarity. Okay.
Yeah.
That's the first one.
To calculate the coefficients in the linear combination of the value vectors.
Yeah, value vectors. And the second one is about homework for the GAN. I found another perhaps error. I'm not sure. since when it runs, it has a debug error, and I found the batch size doesn't match. I can post that onto discussion and
Okay,
email.
yeah, I haven't seen it yet, but I'll look at that.
Where are you getting this error?
Is you also get that debug error?
No, I was able to do the assignment.
Yeah.
I get it in the function run a gun when training the gun.
Yeah.
Is it an error or is it saying they're getting a wrong result?
Error.
Error.
Debug error.
There's very likely something wrong with your code, because it worked for me on the like maintenance, so that's not really fair. But it's also a few other people have already done it and gotten through the whole thing, and figured it out. So there's something there that you can get figured out.
The third is an easy question. So, see, is this okay? So are there any other classes later?
What's that?
So
Are there going to be other classes on deep learning offered by the university? I hope
yeah,
so.
previously, you said today is the final class, yes?
Oh, no. We have next week, we're going to do reinforcement learning on Tuesday and Thursday.
Oh.
And then the final lecture in this class will be the following Tuesday after that. That'll be the week of Thanksgiving. So we won't have a Thursday class. That Tuesday, I'm going to show you a video of somebody who's thought a lot about artificial intelligence and the meaning of artificial general intelligence, and it's giving a counter perspective on a lot of things that you might be feeling at this point, where like you have all these awesome tools, like you're like doing quote unquote AI, but then this guy's kind of reminding us that like we're actually not doing AI yet, not even close. And just kind of bring that up as a counterpoint, just to kind of remind us like what exactly what we've been doing this whole semester. And then we'll have Thanksgiving break. Then the following week, which is the first week of December, is we won't have classes that week, just as it says in the syllabus. That's canceled. That Tuesday and Thursday is canceled. That the idea being work on your projects. Take the time you might have for your lecture and work on your projects. Okay.
So we have 3 classes the whole next week.
Yeah, and then
December 3rd, yes.
Not December 3rd. Just follow the syllabus. You'll get it. All right. Other questions? Yeah, let's go back there.
This is just this is working with machine learning as a job, right?
Yeah.
So one thing I'm trying to understand in this whole thing is like, how do you define like a data engineer and a data scientist? How much are they overlapping?
Yeah.
What are the roles that they're playing in the machine learning process?
Yeah. Right. So I think these kinds of things can be pretty confusing. So there are a handful of companies that employ a huge number of data scientists and machine learning scientists, right? So these are your Bay Area companies and kind of equivalents throughout the world, right? There's not that many. They have a very rigorous system for what it means to be a data engineer, data scientist, machine learning engineer, machine learning scientist, machine learning researcher. It's very well defined and have leveling and all that. But as soon as you move away from those and you get out to like the smaller companies where they can just kind of you can just define the roles and however you want. Like you know what the titles are, but most people don't have a lot of experience with like what makes a data scientist, makes a data engineer, and so forth. I think it can get kind of confusing, right? There can be a lot of kind of overlap between what a title is, but overlap with definitions of other roles and those kinds of things. So I think this is actually like generally kind of confusing. It probably will be for years to come before there's like really good accepted definitions that are more like the definition that you would see maybe like in software engineering job or something like that. But in general, specifically your question, a data engineer, a difference between data engineers and scientists. So clearly both are working with data. That's why data is in the name. But an engineer you might think of as like being very concerned with the movement, and storage, and accessibility of data. So like building the systems around that, which can be significant depending on
on this, the amount of data, like volume data you have. Like this is a serious activity at Recursion. You have a large data engineering team, and their main job, at least these days, is just to maintain and optimize the pipeline of like 50 to 70 terabytes of image data coming off the microscopes in a weekend, and getting that to all the places it needs to go, and going through all the transformations it needs to go to, right? So like our data scientists don't necessarily use the raw images; they're using some featurization of the images. So like a vector, of the images, or representing the images, and doing like the data science work, like statistical testing, and other kinds of analytics. So that's data engineering. Data scientists, is more of like doing the quote unquote science, the analysis, the hypothesis testing, some machine learning, like some prediction, and those kinds of things. If there's a place where there is a distinction between the data scientist and the machine learning scientist roles, then typically that's like the machine learning scientist is usually it's more like on the research side. It can either be on the research side, or it could actually be like far more on the engineering side, where you're still doing, like model training and building, but the expectation is that this person has a lot more of an engineering background to be able to do all the things that it needs to do to really get a deep learning system up and kind of going. I think that's what I've said about these is fairly general and probably applies to most places, but as more and more data science jobs pop up, you just have to go and figure out exactly what they're looking for, because there's just no standardization here. And yeah, it could mean everything from like a statistician, kind of old school statistician using like old time tools to like all the way up through like very sophisticated deep learning techniques or something like that. So, and everything in between. So I think it's tricky. I think it's really tricky.
If you look on like Glassdoor or like any hiring site, you can see like data scientist needs a master's, needs a PhD.
Yeah.
Needs like there's just such a range between what they're talking about, but they're talking about different jobs entirely.
There's a what's her name? I think it's Cassie Kozyrkov. She's the chief decision scientist at Google right now. She has written tons of articles. Yeah, that's who it is. Her last name is Kozyr. She's written tons of articles that sort of try to address this. Lots of people have written a lot of articles trying to address this. I think she's actually done a really good job. I can't point you to any one because she's written like 100. But she has a bunch that are like around, what are all the titles here? What do they mean? She's actually a statistician by training, but definitely whether or not she actually does deep learning, but she has like a lot of understanding about it. Anyways, I go read some of the articles that she has there because I think they're nice and clarifying. I just like her like taxonomy. You can pick somebody exactly with her. She has like 10 roles that kind of go through like analysts to through engineers and expert analysts and scientists and researchers and things like that. And she has it's all written down. I think. If you're really interested, you can't find it. I can probably find it, but I like that. I like her thoughts on that.
Can you repeat her name again?
Yeah, so her name is Cassie. If I'll just write it. There's something right, and it's not right out. It is so Kozyyrkov. I think we check that. Yeah. She's chief decision scientist at Google. Okay.
do you have like follow-up questions on that? Or?
Yeah, so, let's see, so.
Usually the next one is like, what qualifies me for these roles? And it's like, it's even worse, right?
I'm kind of more interested in like the problem, right? It occurs to me you guys have a really complex problem. So how are you balancing like engineers versus scientists? Are you, like, when you hire more data engineers versus more data
Yeah.
scientists?
I think every organization has kind of approached this differently. So Recursion was pretty scientist heavy for a while, but has since been hiring a lot more engineers. There's like lots of reasons for that. This is like software engineers back in front end as well as data engineers and machine learning engineers. And I guess that was because for Recursion there still is a lot to figure out, just like scientifically about like how do we use all this data in ways that make sense. There's the problem we work on is hard. I mean, it's complex, but it's hard because there's the feedback that you really care about doesn't come for years and like hundreds of millions of dollars later. Because when you're trying to discover, develop, and get drugs approved by the FDA, that's a really long, expensive process. So like we won't know for years, unfortunately, whether or not like what we're doing is working or not. There's lots of like ways of kind of getting at that, along the way, like lots of kind of proxy ways of evaluating how well we're doing, but what really matters is getting a drug on the market, and we have 2 in clinical trials right now, and we'll hopefully have a lot more than that, through the next couple of years, but still, it's a long ways from the end on those. Anyways, it started off, heavy scientists, but now it's more balanced, and actually there's probably even more engineers now at this point. But every organization can deal with that, how it makes sense. And like a lot of that too depends maybe not on like the problem you're working on, but just who's in charge, right? Like and how they think about how to solve problems and things like that, right? Like a software engineer or someone with a deep engineering or systems engineering background might tend to hire more people like that because they tend to solve problems in that way, right? Whereas another person who's coming from like the research side might have more like that commitment to solve problems that way. So every organization's got a different way of thinking about this. Whether or not they're like consciously thinking about it, it's very subconscious. Cool. Thanks. What other questions? Yeah.
Yeah, question is about Transformer. So currently, my project involves to generate representations for quite a long text, maybe 5,000 words. So usually, other NLP techniques like RN or even the vanilla Transformer does not fit in this requirement. So I'm thinking if there are any Transformer-based method to generate representation for such a long text. So there are some variants of Transformer like XLNet that is more capable of dealing with long text, but not as long as such like 5,000 words.
Yeah.
So my initial thought is to, first generate representations for like sentences, then maybe algorithm take average to generate representation for paragraph, then to the whole article. So is there any better choices?
I mean, there's lots of different choices. Like whether or not they're better just depends on how well those choices
I just
perform.
want to know if they are.
I don't do NLP on a day-to-day basis, so I don't have a good intuition for that. I know there's lots of things that you can pick up and try to do, but because that's not like something I do day-to-day, I don't really have a good educated, say like, oh, here's what I would do. I like to just go pick up the things that seem to do, like everybody's talking about, try to get those to work first, and if those don't work, I would, like breaking the problem down, like what you're doing right now is probably a good idea. Although, the power of doing these things is to not just average representations over, some body of text, right? Like that's like you're gonna lose a lot of information, right? In that operation. So, try some other techniques. But I don't have a good, I don't have something good to tell you there.
Okay, so a quick follow-up. So when we are fine-tuning say, a BERT model, so we only fix the last layer of the model, or we only allow the last layer of the model to
That's a typical way of dealing with it, yeah.
Oh, wait, okay.
Yeah.
Only
Right.
the last layer.
Yeah, so I mean, it's your, like wherever your encodings are coming from, you want to be able to learn, you know, at least the weights of your encoding layer, you want to be able to fine tune. And probably, you know, a little further back than that as well, just depending on how different the data set is from the one that the model was pre-trained on. Right? So if they're very similar, you just need a little bit of fine tuning so that, you know, just adjusting weights in the last layer probably. But if it's a lot different, then you want to work kind of further in. And like the idea there is that you're relying on the pre-trained network to like produce features for produce features that make sense in a similar data set, and like, you know, and just allowing all the transformation that's happening throughout the layers to still remain in effect. And then you're just taking whatever that output is and saying, okay, I know this is like got a lot of information, and now I'm going to just now use whatever information is there and, you know, fine tune it and just adjust it slightly for my particular problem. So it's like, if you think about it, it's something like all this stuff was trained on some like this distribution of data. Now the one I have is another distribution, and if they're really close, I'm going to be great. But if they're not, then I got a lot of my network to try to go from this one to that one. And fine tuning is a great way to go about it. There's actually like tons and tons of domain adaptation techniques for, if you do have these kind of source target pairs, like these things came from this distribution, this one came from another, but that these pairs of things kind of have something in common. There's a lot of ways to kind of to learn to take one distribution, kind of move it to the other one, so that you have quote unquote more samples from the target distribution, the one that you're trying to learn. There's a lot of work in that area, and we haven't really done anything like that in this course, but there's tons and tons of work in that area. It's called domain adaptation, so I could try to poke around there a little bit. But I haven't heard anything about that for NLP. Cool, yeah.
Okay, so one thing I've heard from mentors is that biology is an immature field, and that's why it's a good field to go into because there's a lot of room to grow. What about computer science and machine learning? Computer science does seem like it's mature, and machine learning, especially this deep neural net stuff, I just don't have a gauge for how mature it is. Since you've been in this for so long, how do you see it continuing to grow, right? And then how advanced do you think these tools are going to get, and is that going to make it so you don't have to be as scientific or rigorous in your training to actually use these things?
That's a good question. So I think there's a lot of people who want to believe that like we won't need data scientists. In a couple of years we won't need data scientists. Like everything that data scientists do right now, like we'll just write software that learns to do what they do. So and in some sense, like that sentiment is correct in when it just comes to very simple kind of data science tasks. So if this is something like, here's a tabular data set, here's the training data, or here's what the samples look like. Here's the thing we're trying to predict from these. There's lots of like what are called AutoML tools, so automatic machine learning tools, where you can just give this kind of data set to these tools, and it will. There's a couple of flavors here, but the basic idea is like it'll train on a whole bunch of different models. It will pick the best one, maybe it might ensemble them with the task, and then all of a sudden you have this like predictive model that's doing really, really well. So like H2O.ai is a product like this. Data Robots are products like this. Google Cloud now has an AutoML feature or an app. I mean, what's that?
Big squid.
Oh yeah, right. So there's a lot of these. There's a lot of that that exist, and like for very simple machine learning problems like that, like it's true. Like it probably is just better. Like it certainly is cheaper to just let a machine kind of go at it. Don't get a data scientist involved, and then as long as you get kind of like good enough result from that, then you're happy. Unfortunately, like I think those kinds of problems like are boring in like to begin with in some sense. Like if these algorithms can do that, then it's not that interesting of a problem to begin with. And we should use as many automatic techniques as possible. But like there's so many problems that you can't do that with. I mean, there's just tons and tons and tons, right? So the difference is something like it's not like the problem just can't be posed as a simple like supervised problem, right? And the reasons might be you don't have enough labeled data, or you never will have enough. You'll never have enough labeled data, or the labels are bad for whatever reason, or really so like things that get into like the area of representation learning, where what you really care about is like representing something in another way. Like often those types of problems aren't, they don't have a straightforward. It's not just like a straightforward function approximation task that you're trying to do, and these require a lot of just know-how right now. Like, and so is it the case that like these AutoML things will get better and better and like be able to move into harder and harder problems? Probably. Like, but that's great. Like we want those tools to exist, and we want to be able to use them and know when to use them and throw them at things, so that we don't have to like spend our time thinking about that when we think about the harder problems. And so yeah, like anybody who's kind of doing that kind of more simple kind of data science or machine learning is, like they're not going to have jobs, I guess. But we surely don't have artificial intelligence. We do have very good function approximators right now in neural networks. And they do a really good job of learning the statistics of the data sets they're trained on. But there's nothing out there that does well at like generalizing outside of those very, very much. So, companies that do really well with machine learning applications usually have control over the data set generation that they're working with. They control that in such a way that it relieves the burden of the machine learning system of having to like adapt to like all kinds of different distributions of data, and they can generate as much as they need, I suppose, to within constraints. And so, yeah, these things will continue to get better and better and better. Machine learning will get better. Like just the algorithms, but we're a long ways from like some leap where all of a sudden it sort of takes over and does all the thinking for everybody. And I just would be really cautious of people who think that that's what machine learning is, because it's like machine learning is just another tool for scientists to use to solve problems. And if it's if it's the right tool for that, then great. And if it's not, then you have a whole host of other tools to use, like statistics. Statistics is still a really important, extremely important tool of a data scientist, because most of what we do is most of the questions we're trying to do, or we're trying to answer, we're trying to make these decisions with a whole lot of uncertainty. And statistics is a way, just in general, a way of kind of approaching that in a systematic and rigorous way. And so much of what machine learning data scientists do these days is just prediction, without any thought of like the uncertainties involved. And those kinds of jobs, like that kind of an approach will go away, because if you don't need to think, then yeah, we can automate it. But the good problems, the hard ones, can't be automated. I was rambled a bunch on there. Come back and just ask again, like, was there anything there that I didn't address in your original question?
Yeah, I'm kind of interested in the maturity, right? How mature are we right now? Are we going to get like an Excel-based application that does this?
No, because, I mean, what you can have, so look, what you can have is, so it just depends on like what you have in mind. So you're never going to have Excel-based application that's going to like train on images, right? I mean, this right now requires like a whole bunch of computational, hardware and like know-how, like engineers who know how to put all the pieces together so that you actually have a chance of doing that. Cloud-based systems are making this even easier. It's amazing like how much like I/O speed you can actually get out of like reading up data out of like Google Cloud Storage buckets or AWS buckets. That's pretty amazing. But still, we're a long ways from this being Excel. Now, what can you put into Excel? You can put in Excel on like a trained neural network, right? Trouble is that Excel already uses up so much memory that you have to find some additional memory to put the network in. But people work a lot on like how to take a trained network and then distill it or compress it so it takes up it's getting so you now have another function that gives you that near the same accuracy or whatever, but in a smaller number of ways or just smaller than this. Like that, like a lot of that already happens with your phone. In terms of like all the apps that are doing fun things with machine learning. But I mean, that's just like someone else has done the hard work and just brought a function over to Excel. It'll never get past. I mean, like the dirty secret of deep learning is like how costly it is to do it. Right? It is really expensive to do it, and this is why like the progress is actually made at the companies who have annual revenues in the tens of billions of dollars, because like it costs that much to. I mean, it doesn't cost tens of millions of dollars, but like the research plus all of the engineering and hardware involved, it's really expensive, and it's really the carbon footprint of these things is it's horrible, right? Like these, I don't know if you've ever been to a data center, but it uses a lot of energy, and this is what we throw. We have these servers that have 8 GPUs in them each, and they're all drawing 300 watts, and plus all of the high-end networking. I mean, it's really, really expensive. So what we do right now is like a really expensive hammer for learning, a crazy number of linear transformations with a couple of nonlinears in between. That in no way is intelligence. That is not artificial intelligence. That is a function approximator or a distribution approximator. We're so far from the real stuff. But it's really exciting. I mean, we can do things now that we never could 10 years ago. And like with amazing, astounding accuracy, or just ability to, I don't know. Like it's obvious that this stuff is really, really work, but it's like something else is going to have to change for this to be like a tool that like everybody has their Excel and all know how to use it. It'll have to change. Like we can't use stochastic gradient descent on neural networks. Like something else is going to have to change. And maybe that becomes like, we just get such powerful GPUs that are super energy efficient. I guess that can happen. We just keep doing things the way we've done them. But something else would have to change to get past that so that we really have, like serious compute. That's of course just my opinion, not endorsed by anybody else but myself. And there's definitely a lot of people who think totally differently from that, but I certainly don't see it. Beyond that, let me say one more thing on that. And this is me rambling now, so stop me if this is like not useful, but everything we do right now is like ultra empirical, right? So there's not like a guiding principle that says like, oh, here's the problem, here's how you solve that. I mean, it's basically like, do you have images? Go grab a CNN. Do you have text? Go grab an RNN or a transformer or something similar. Is this like, are you trying to learn like the action to take given the state of your system, go pick up, some combination of these things and train it with reinforcement learning. I mean, that's the extent of it, right? And then every year, there's new papers come out saying like, hey, check out this new architecture. The blue score, we do much better on this, English to French translation, or the blue score that actually is taking into account language and text. I mean, well, that's awesome, and it's a good way to try to measure progress in the era that we're in. It's by no way a proof that this is doing something that you're really doing. In fact, so much research has come out showing that convolutional networks in particular have been trained via supervised learning. They don't do anything like people expected from them. There was always this thought that you're actually building up features of the image, and it's going from edges to pairs of edges and color gradients and things like that. But it turns out that there's a great paper that came out last year, super awesome paper that came out. You can actually just get rid of all the color information from your image, and everything is just totally fine. Color doesn't matter at all. And you can actually get rid of everything but some basic texture information, and you can do almost as well on image there. So it seems to be picking up on something fairly high frequency texture patterns to tell if this is a cat or an elephant, and not anything about there's these points that represent ears and and a long trunk, it's abstracting to do that, nothing to do with it. It's actually just basic textures. Really, really, really cool stuff. Really cool stuff. Yeah, so the paper, I'm kind of forgetting now, but it's something it's really a great paper. It's you swap out, you take the textures from one class, and you use those in the with the outlines of another class, so elephant in the cat class, and then these things that have the elephant textures are predicted to be elephants. And it's one of these great relation studies that just makes you go, what's going on? I don't know, we don't know what's going on. And we all humans are super good at telling ourselves stories about how things really, how things work. But without an underlying theory that you can statistically test and invalidate, we just don't really know. So this whole thing is empirical right now, right? Bert gets replaced by Ernie, the next day, and the next year gets replaced by something else, and then somebody comes up with linear architecture and gets replaced. People are just kind of keeping up with whatever's the coolest new thing. It's empirical. Right now, this is just a great tool for doing prediction and a couple other kinds of data learning tasks. But beyond that, it's just a mess of linear algebra. Other questions?
So it's kind of feeding on the same thing that a lot of you answered. So if I understand you correctly, you're kind of saying that deep learning is a very niche thing, and it's not for everybody. It's very few companies out there are going to be utilizing it. Is that a correct kind of interpreting what you're saying?
I mean, so don't take what I've said as wow, deep learning only matters for these couple of tasks. People are figuring out how to make deep networks work in a whole lot of situations that are really interesting. But the truth is that these things only work when there's enough data, there's enough relevant data, which most people don't have. That's labeled in an appropriate way, which most people don't have, and a lot of know-how how to do empirical science like this, and that's maybe the hardest part. I mean, when you finish this class, you'll be familiar with a lot of architectures, and you have just a tiny bit of experience training these models. But the real work comes next in getting a new problem and trying to go from 0 to really top accuracy on a prediction problem or something similar. And that's a whole other black art that we're not even spending time on, because it could take a whole semester. And it would be a really fun thing to try to teach and and definitely learn, but it's definitely just more empirical black art. Once you're doing it, this guild over here, does it this way. this field over here does it this way, and who's right and wrong. It's always the way that's always decided is how well do you do on this task, like with this data set and this way of evaluating it. And that's there's nothing wrong with that in the sense of like fundamentally that's fine, but it's not getting at some deep understanding of like when I get a new problem, how do I actually solve it with these tools?
Well, so currently our model has gone to pretty large. And there's another trend, and which is called model distillation. I heard, and so one way is to decrease the precision, like to 32 bits to 8 bits. Another is to create a student smaller model to learn from a teacher model. So what do you think this trend will go in the future? So what is?
I mean, so distillation and kind of like the related ideas there, like they've existed for a while and they make a lot of sense, right? But again, there was a precursor to this, which was training a big model first and then distilling it, right?
Right.
So, I mean, so statistics is this like, so when you do statistics, like you have this hope that like your linear models are somehow good enough for predicting the phenomena in your data set, right? The trouble is that like, except for in very few cases, that's not the case. So we now have these like really awesome tools that are like so highly parameterized, right? So like when you have, like in these GP2 or GPT version 2 models that have like 1 billion plus parameters in them, like that's a lot. That's a long ways from like our multivariate Gaussian that had, in 3 dimensions had, three you had 3 entries in your mean and 9 entries in your covariance matrix. Or I guess not even that many because it's symmetric, but like, we're a long ways from that, right? And so we have no idea what's going on. People are working at it, and there's some like really interesting kind of progress, but in reality, we don't have any idea what's going on in these billion dimensional parameter spaces. We just have heuristics for how do we get these models to like get to a local minimum that like is performing well according to whatever metric we picked. Yeah, I mean that's the state of it, and it's awesome. It gets us like we can produce celebrities' faces that never existed, or anybody's face never existed. And there's scary things you can do with that, like the deepfakes stuff. And I think that's concerning. Like, it's powerful enough, but it's also, if you think about it, it's also just because we're so willing to engage with a 2-dimensional medium, like videos and with additional audio signal. It's us that are the problem. We're just so willing to do that and believe that, and accept it as like the source of information. That's really on us, not on necessarily. Well, if you're doing deepfakes for malicious purposes, that's on you. That's bad. But I mean, like in general, it's only because we engage with the world in this way right now. And if we engage with the world in a different way, that won't work. I think you had a little bit.
Yeah. So, kind of like going off the last thing we were talking about is. So it seems like if you like encapsulate, deep learning is good for problems like big data. Is that saying big in dimensions? So like an image has many elements in the array, or you look at something like you have like many millions of rows of or like entries of but only like 100 dimensions or something like that.
Right. So I think the way to think about that is something like the following. So your problem or your data has so many degrees of freedom. Okay. So just because it's got like if it's tabular, if it's got 100 columns, it doesn't mean necessarily there's 100 degrees of freedom in that. Right? Like they're not necessarily all independent of each other. Most data is correlated in some way. Like, it's just, it's, we only have so many ways of measuring things, and and as a result, things often get correlated. So that reduces the number of degrees of freedom. So if you think of every problem, try to formulate every problem somehow like learning the distribution of the data you're looking at. The degrees of freedom are basically saying like how many parameters are needed to parameterize this approach. So like I have some model that represents a distribution. It has so many parameters. So you could have 100 dimensions, but if they're all sampled from the same Gaussian, like one-dimensional Gaussian, then I got 2 parameters to learn. Right? But it can be far more complicated than that, right? So the more degrees of freedom you have, sort of regardless of the number of dimensions, the more data you need to learn that. And if you just think of every neural network as like representing a family of functions, and then basically the data's job is to shape those parameters within that. So let me say that one more time. They're functions that are parameterized by X number of weights. So and those again sort of represent the degrees of freedom, although obviously they're way more than you. We can create huge networks. So there's definitely something else going on here. Like we're definitely over parameterized for most problems. You think about these huge models trained on like MNIST, like there's a huge difference. But like you need an amount of data sort of comparable, that's sort of like scaling in some way with the actual degrees of freedom in the data set that you're trying to learn. And you can't, like, it's hard to know that a priori. In fact, there's almost a problem with a priori. But that's, like theoretically, that's kind of what I think about it. So the more degrees of freedom there are in data, the more data you're going to need to be able to help you shape the higher number of degrees of freedom in that parameterized family. So when you're getting started on this, you want to pick a network that's where like some instance of that network. So like some choice of all the parameters is either the function you're trying to approximate or like really close to the function you want to approximate. If it's nowhere near that, like you're sunk from the beginning, right? This is part of like the empirical part of this. But if it's somewhere there, then it's really just a game of like how much independent, well-labeled data you have access to be able to shape those parameters. It's a lot more because like there's this black art of like having any of these super over parameterized networks to like converge to something meaningful, but there's people figure out ways. So that's like a really loose answer to a good question, but there's I think that's like a framework in which to think about these things. It's not like a strict, n number of samples, p number of dimensions kind of thing. Unless you can ensure that like you have independent columns. And when you have tabular data, there is a way to do this, right? That is like PCA will give you independent columns, but that really quickly gets at the degrees of freedom, right? Like the amount of variance explained will drop off really quickly and pretty soon you'll just have just noisy dimensions, right? So like chopping that off, then you're in good shape. You can't do that kind of stuff with images. You can't do that kind of stuff with text. So you're expecting the networks to sort of like figure that out. Yeah.
So kind of going along with that, we talked about this a little bit earlier this semester, but we have like the option to take our image and have the convolution that's produced our dimensions, like we kind of brought up. But then we also have the other option, which is to produce our own dimensions with maybe our own intelligence.
Yeah.
Then from there, at least a little bit of experience that I've had is like playing around with like lasso, elastic net, regression techniques to figure out what dimensions are meaningful. So I guess my question right there is, what about these traditional techniques and how can they like help us feed into this?
So the real clear answer for images is like traditional, like handcrafted features of the images. They're just totally inferior to
to learn features from a good convolutional network, like trained well with a good task. Like that's super clear. We left, what was it, like 20-something percent accuracy or error, like, or 20% error rate or whatever from like in 2011, the final time that a handcrafted feature extraction mechanism worked for like an ImageNet. We went really quickly from that down to like, past human, lower than human error, just in a couple of years. So, images, and there's lots of different kinds of images. So this isn't true for like every single image you could take, but like images in general, because of their high dimensional nature, neural networks just are going to always work. But when you get like tabular data, it's usually the case that like when you're working with tabular data, that like some sort of tree ensemble is going to be better than a neural network on the tabular data in any sort of prediction task. And I don't really have a good answer for you, but I've experienced this over and over and over again, and lots of people have it as well. You can't train very deep, like feed-forward networks, fully connected networks. So, like starting from a vector of input, and like 2 or 3 layers is usually optimal. If you go beyond that, it's usually usually you're hurting your performance, and it's almost always the case that you pick up like gradient boosted trees and training that, and that's going to do as well and usually better. Like why is that? I'm not totally sure. It has something to do with the fact that like with images, especially with like natural scenes like an ImageNet, there's just so much going on in that learning the statistics of those kinds of images, it's not just like a simple decision tree or ensemble of these things kind of dividing up the pixel space. Like the whole approach, using convolution to learn spatial filters that are meaningful at these different layers of abstraction is like the right approach for images. But like that same kind of idea does not apply well to tabular data, because the relationship between the entries in your data is like, it could be anything. Whereas if there's images of like natural scene, like that's really constrained. Even though like there's a lot going on, there's a lot of constraints happening there that are happening at like a different scale than we're able to really kind of describe well. Like these networks really well. And yeah, it just says something about the fact that like if you think of like tree ensembles like gradient boosted trees or random forest, something like that. Like that kind of like the parameterization there is sort of like optimal for optimal is a strong word, but it's like it's already it's already kind of in the optimal area for working with tabular data usually, and it's not requiring the network to kind of learn some set of parameters that where it's trying to be optimal. Like it's usually having a hard time. So I don't know. I can't remember what the original question was there. But
yeah, I mean, definitely answered.
Yeah.
But I mean, like, so the technique you use for tabular data, how much you're taking an image.
Usually, yeah.
So,
and text too, right? Like text is another good example. Like the statistics of language are really difficult to sort of write down, like all the rules, for producing features from them. And again, recurrent networks do a really good job, and now just these attention networks like transformers do a really good job of being able to learn those things. So it's sort of like, I don't know if it makes you like feel happy or sad or what when you hear things like that, but what you should think is that like, oh, that's good. Like there's lots of tools in my tool belt, and I'm like part of your education is this is like everything you get into is when to use which tool. Definitely coming at it like the hammer approach is a really bad idea, because it's going to work great for some things. You go take a convolutional network to you tabular data, it's not going to work out.
Yeah, so currently we have image model and we have language model, and arguably they are independent in the sense that the language model only train on text and the image model only train on image. But that's not how our brain works. When we read the word cat, not only we read the word and we also come up with the image of cat. So is it possible that a model, say a language model, could also train both on text and image?
We've actually seen examples of this kind of thing, sort of like when we were looking at the captioning of things. So that's a different kind of problem where it's like the input is the image, the output's the text. So you're learning the relationship between the pixels and the text that ought to be generated, right? That's a little bit different than what you're saying. You're saying something like, we create a representation of, say, cat in our minds, and we kind of get to the same representation whether we see a picture of a cat or we read about a cat, right?
Yes.
And that's so there's so you can imagine setting up networks to like embed images of cats and text of cats in the same space. The trick here is that just like with humans, or like most species having both an auditory system and visual system, there are two different systems. Right? There are two different inputs, and so like our neural network is already really good at like taking one kind of input and dealing with it, taking another kind of input at separate times, not necessarily together, right? With neural networks, like the way that we train them, they are not very good at like taking some pictures of cats and then some words of cats, and then like at a different time. Like usually when these things get trained, it's like we want to have a pair of these things that kind of fit each other. So that's not necessarily true. I mean, you can imagine like jointly training two networks where they ultimately end in the same like embedded space, the same sort of latent space where like representation of cat exists, and in this batch could be a batch of like both images and of text, and you have an additional constraint that like when those two are together, like that embedding, where this embeds in your space, you can like push those together. For instance, like a metric kind of learning that's called, where things of the similar class ought to be close to each other in the embedding space, and then things that aren't ought to be pushed away. But there are definitely ways of going about this, but this is not like a very natural thing for neural networks the way that they're formulated now, right? It's very natural to have even if we have a multimodal data set, so like text and images, our networks usually need to have a way to input both, which means that both at training time and at inference time, you also need examples of both.
Yeah.
Right? Which is very different from like the way that we work as neural networks.
Yeah, I'm just thinking, well, if taking more Arduino model courses will improve the performance of models.
I mean, it depends what you mean by improve. Like, if what you're saying is that we have better representations, what does it mean to have better representation? Like, what's the task you're going to use? The way it works for us is that somehow we don't sound stupid when we have a conversation about cats. I mean, that's really what it comes down to. Right? Like, it's clear that I know what a cat is from both seeing it, hearing it, reading about it, smelling it, hopefully not tasting it. Right? I mean, like, and my feedback is I have this conversation about it with you, or like we plan to do something with respect to cats, and like we actually do that. Like we're very like task. We evaluate ourselves on like how we're able to use that information. We have a proxy like that for neural networks, but it's totally a different thing, right? It's like it's very specific to like the way that the model is trained. Somehow we're like a lot more general than that. I mean, and I say somehow, I mean there's clear and obvious ways that we're different, a lot more general. And again, like it's not like artificial intelligence has to look like us. I don't think that has to be the case. Like, but we'll know when it's doing the right thing when it can sort of like plan to do something on its own, like independent of our having programmed it like, like planning a goal and achieving it is going to be one of the main ways that we know that this thing, like, that we're seeing intelligence, right? And at this point, we're a long ways from that.
Just as to add on to that, it's like a counter argument. There's like AI researchers that kind of feel like there's nothing, that there's like generalized intelligence doesn't exist, and everything is localized intelligence, and everything, like, you think people are generalized intelligence, right? But you're really designed to exist in a world where you can feel and touch and see, right? But like trying to imagine something that's more than 3 dimensions, you can't do that very well. Or like basic statistics, you can't really you can get tricked by those kind of things. So their argument is basically that people are localized intelligence machines designed for the world that we live in, and to try to like create a generalized intelligence is foolhardy because everything is localized intelligence.
Yeah, and I totally get that, like, from, like, I get that argument completely, but I guess when we talk about generalized intelligence here, like, we are sort of saying something like, able to like autonomously like operate within whatever world we put it in, and that could be like we give it sensory system, like a visual sensory system, and whatever other sensory system we want to give it. And that could just be like, reading text could be a sensory system, right? Like, it's just a way of taking data and processing it, and then using that, like representing it and using that to plan. But, we don't even really have great, I mean, just kind of going on this further, we don't even have really great language for saying, like, what it is that makes us intelligent. I kind of give you this coarse idea of, like, we'll know intelligence exists when we see something like plan a task and execute it autonomously, right? Under certain constraints, like it has energy to consume, like just the same way that, like, we have to have energy to be able to do these kinds of things. So we eat, they'll be plugged into, the socket and things like that. But what we have right now, like all the things that you're learning, even like the state-of-the-art things that you're learning, this is not intelligence. These are really excellent systems for learning the statistics of the data sets they're trained on. And there's always the argument of, like, well, isn't that how we are too? Like, these are the statistics. And that's, like, in some sense that's true, but we learn that if that is all we are, we learn it at a much deeper level, right? Like, we learn it, like, I'm able to tell that you're a person, and I can generalize a whole bunch of things about what it means to be a person, and therefore I can operate with you. Like, if I'm trained on the data set with people in it, like, what we're doing right now, like the kind of thing I experience is just like, what does a person look like in a 2D image, right? So, like, we don't even have the right data for these things to learn yet at the scales that would need to be learned to get to these things. So, yes, these algorithms are learning to play hide and seek really well, in certain constrained environments, but again, like, it's just for that task. It's really hard to, like, go from that task and then generalize it to all the other things that a machine could do.
Yeah, speaking of the statistics, and we see that the neural nets are learning the statistic distribution of the data, but actually we don't have so many statistics going on here in the model, so that's totally different from maybe 20 years ago, when the model are maybe dominated by the Bayesian guys.
Yeah, but when I say statistics, I just mean like the correlations in, like, whatever the input is, like having learned correlations actually a bad one to use, but like having learned the dependencies of the input data to say something meaningful about it. So, like, to say that there's a person in it, for instance. Like, I learned something about, like, how this data is distributed and where the people are in this distribution, right? Like, that's really what these things do.
So, but do you think maybe the Bayesian code things will back to power, or I don't know?
That's just another tool in the toolbox, right? Like, that's just a tool for saying, like, how do I incorporate prior beliefs in my estimation of parameters? Yes. I mean, that's a really basic way of thinking about it. That's really what Bayesian statistics is, right? And there's a lot of techniques for it that fall in that category, but That's what it is. And we have techniques like that in deep learning, right? Like, like the autoencoders are ways of trying to infer estimate the parameters of the factors that generate, data and things like that. So it's, the same ideas exist, we go about them in different ways. And we use Bayesian ideas in deep learning. We formulated like the variation autoencoders in that way.
I also have seen Bayesian GAN, which use.
Yeah, lots of people. There's always like for every like great network architecture that's out there, someone has a Bayesian paper with it, like how to incorporate prior beliefs, distributions like prior distributions on parameters and models.
So I just wanted to talk a little bit more about. So you've mentioned like we've been talking about that. All of this is really just kind of inducing functions and distributions and such. But there is kind of a desire to get something more general that's getting deeper inferences. Is there, obviously there are probably many people within the community that are seeking obviously the same kind of things. What kind of directions do you think are most promising? I mean, is it just so? I'm more familiar with what kind of NLP research, and you mentioned a variety of models and such, and there's always a criticism that it kind of just seems to be that the next best model is just deeper and an extra billion parameters or whatever, right? And there's kind of been this communal neural architecture search that's been fairly prominent in the last. It seems in the last several years to get even better at this particular approach. But it would seem that maybe you're skeptical that do you think that this kind of continuing this style of approach we will approach.
I mean, I think there is a possibility in the limit of enormous computational gains, enormous like data set sizes of like huge varieties, and advances in architectures that allow for sort of these multiple often censored inputs, for training these powered stuff. Maybe in some reinforcement learning type of way, which is like, I have an objective, and I'm getting better and better at this objective. But again, like for it to look general, like for there to be something in there that's like, it gets really philosophical at some point. Like you might, you kind of want to talk about the consciousness and like that, but like forget about all those kinds of things. Like, there's a lot of ways to think about this. Like, so one approach you could take is to say that's all we are. We're just like really awesome. Like we're just really, really able. Our genetics, we've evolved in such a way that like we're just really, really good at surviving in our world, and we're just a bunch of algorithms for taking in the kind of data that we expect, like that is in our world, and being able to stay alive. And so you can imagine kind of replicating all the things that enable that for us. And then maybe being able to train that in such a way that you get to a point where like the thing is kind of like us. Not that intelligence has to be like us, but just as a way of kind of grasping this. So I mean, I guess it could happen. Like if that's really what we are, then yes, it could happen because we're obviously like a positive example of that. Is that what we're doing right now? No, it's not. It's not even close. There's a lot of big differences. When it comes to like things like really difficult to talk about scientifically, but that are interesting to think about from a human perspective, things like consciousness, like will these things ever have a consciousness? Say like that's really convinced that there's an I right here, like or an I in the algorithm, and that like I'm keeping myself alive. Like will that ever happen? I don't know, I hope that we can one day talk to an algorithm and find out. Well, I'll ask it, you know, what it's like to be alone and what it's like to be, you know, maybe we'll view it with emotions and things like that, or give it like a, what's the system I'm trying to think of? I can't think of it right now. But we'll do it with you know, like chemical feedback systems that you know, tell it about the state of itself, and yeah, maybe it'll get lonely and depressed, or maybe it'll get like excited and hyped up, I don't know, but those things aren't necessarily intelligence either, it's just a way of reacting to the environment. So we're, you know, if that's all we are, then yes, like you can imagine that like that could happen, right? Because we're a positive example. If we're more than that, then no, right? So that's a problem we can't really answer scientifically just yet. So it's definitely not great. But what we're doing right now is nothing close to that. And it's definitely like a scale thing. We're on a different scale. It's probably more the algorithms we use to learn. Like we require a lot of data to like know. It requires a lot of data right now for any sort of reinforcement learning system to learn to like not like to do its objective. But humans are really good at staying alive, like that ultimate objective. Like we're just really, really good at that. We might be like a really great pre-trained neural network, right? Like that's what genetics is all about. But we're really good at it. We don't require a lot of examples, and we generalize super, super well to like all kinds of tasks. And we learn to do one thing, and now all of a sudden we can do a whole bunch of other tasks. So people are definitely approaching this from approaching what